In this video, we are going to focus on the first component made up by semiconductor materials, the diode. Diodes are based in a very simple idea: to let the current crossing in one direction and avoiding the contrary one. Please notice that this is not a non-linear device. Up to now, every component you knew was a linear one, able to modify the amplitude of an electrical signal, but not its shape. Resistors that attenuate the voltage falling along them, or capacitors or coils, which introduce a phase difference. Every current versus voltage curve is a straight line, because at the end, the Ohm's law of proportionality is behind them. I will use this opportunity to mention that this one is a characteristic curve of the device. Diodes are the first components that don't follow a straight line at all. In fact, this one is the curve for them. There is an interval where any current is crossing and another one where the current crosses free. This was made in the first half of the 20th century by an incandescent filament emitting electrons towards a metal plate in the vacuum. It is to say, a traditional light bulb with a metallic plate. Electrons could go from the filament to the plate, but not backwards. After some time, a semiconductor diode could be constructed. In this video, we will see how this diode works.
Let's start with a PN junction that you already know. We have two contacts or pins at both sides. The one at P side will be the anode. The one at N side will be named cathode. In an actual diode, the component has a mark at the N side or the cathode. In fact, the symbol is like an arrow with a barrier. The arrow points the direction of the current from anode to cathode. The inverse one is blocked. Let's see how it works. We are going to start at the moment in which the junction is formed, for instance by the fusion. Let's imagine that we are seeing a snapshot of that very instant. Then, looking at the center of the junction, the negative carriers, electrons at the N side, are recombining with positive ones, holes at P side. No free carriers appear just at the junction. A depletion zone, where any free carrier exists, appears. There, an electrical field is created because there are positive ions in front of negative ions, fixed in the atomic network. Plotting the voltage of the electrical field that is created, a barrier of 0.6 or 0.7 volts appears. This is an electric potential barrier. This is a gap that needs to be jumped by an electron to cross to the other side, or similarly by a hole to cross to the other side due to the rejection created by the ions that are in that side. Once balanced, the junction has a null net flux of current. This one is the symbol of the diode for drawing purposes in a schematic of a circuit. It is an arrow indicating the direction of the current and a barrier standing for that threshold voltage that carriers must jump. Let's bias the junction with a voltage. This is to say, address a voltage to its sides, allowing or not a current to cross the junction. Carriers are not able to cross the junction by themselves because of the barrier. They do need a help. That help is applying an external voltage, an extra energy that allows them to cross, to overcome that electric potential barrier. With a positive voltage between P and N sides, we get a double effect. Think it with charges. They are repelled by the applied voltage, so they tend to get closer to the junction, no matter if they are positive or negative. Negative charges are repelled by the negative voltage. The same with positive charges and voltages. The physical effect, the depletion zone is now thinner. Regarding voltage, the barrier has been removed. Electrons can cross it easily. To get this situation, the external voltage should be at least of the same value as the barrier. As current takes the contrary direction, that negative charge, then going from anode to cathode, we have made a forward bias of the junction. The barrier is also called the forward voltage by this reason. Let's imagine the contrary situation to make an inverse bias. The voltage to be applied is reversed to the previous one, negative at P zone and positive at N zone, favoring the voltage barrier in fact. Charges are going to move towards the contacts, because they are attracted by those voltages. There are more ions of the network contributing to the electrical field. That increases the depletion zone, leaking out their surroundings of charges. That zone without any free carrier is now thicker. Regarding voltage, the barrier is higher too. In that situation, the only current that could appear is the one produced by increasing temperature after an electron-hole pair generation in the silicon. The electron is under a strong electrical field, here for instance, and then it can move towards the cathode as soon as it gets free. This so-called reverse saturation current is on the contrary direction than the forward bias, but anyway, it is negligible. Now, we can understand the current voltage characteristic curve of the diode. Forward bias. It is an exponential curve. Once overcoming the forward voltage or potential barrier, there is, in fact, a knee around that barrier at 0.6 or 0.7 volts for silicon or 0.3 for germanium. Shockley equation, this one, stands that the current crossing the diode is the product of the inverse saturation current and an exponential. The exponent has got the voltage in a numerator and the thermal voltage in denominator. That depends on the Boltzmann constant, temperature and electron charge. Thermal voltage is around 25 millivolts at room temperature. Reverse voltage. Diode is not conducting. We are in this area and there is a minimum inverse current of saturation, mainly negligible, nanoamperes. There is an extreme zone, here it is, where the current is what the circuit demands. If it is regulated by fabrication, it could be named center zone, and the voltage of the junction will be constant, no matter the current at the cross. The center voltage. On the contrary, the diode can be damaged. This would be the breakdown voltage. When using the diodes in circuit analysis, using the exponential equation would lead us to transcendental equations and a big mathematical mess of numerical methods. We will use a model instead, a circuit that can model what is happening in the junction and thus using it as a black box. Analyze what is happening in the rest of the circuit, then using the model of a diode is replacing it with a schematic circuit that behaves exactly as the diode will do in the circuit, at least as an approach. Then we will make approximations to the actual characteristics. The first approach is the one of the ideal model. This is as simple as replacing the characteristic curve by this one. An off zone, reverse bias, where the diode does not conduct, there are no current through it, and an on zone, forward bias, where the current is not limited by the diode, but by the rest of the circuit. We can draw again the picture of the diode in the circuit, but instead we are drawing a piece of circuit that represents exactly this behavior, and we will use it as a simple piece of circuit in our analysis instead of the diode symbol. It is easy, isn't it? For instance, think over the forward voltage zone. As the current is not limited by the diode, we can substitute it by a simple wire, a short. In the reverse bias, as any current can cross, we will replace the diode by an open circuit. The second approach is closer to the characteristic. It is called a real model. We will name it M1. In fact, the point is only that the reverse bias area is extended to the forward voltage or the barrier potential. Then the diode can be drawn again and the reverse bias is exactly the same as before. Look at this part. An open circuit here. But now the forward bias zone must be represented by that forward voltage, and then the diode will be replaced by a voltage drop, exactly the same as the forward voltage or the barrier potential. While the diode is conducting current, the voltage falling between its terminals will be the forward one, from anode, higher voltage, to cathode, lower voltage. The third approach is similar to the previous one. It is the real model M2. Now, the point is to draw a slightly bent line from the forward voltage on. The small slope is to simulate the exponential zone of the forward characteristics. Then, the model should be again the same for the reverse operation. As you can see here, an open circuit can replace the diode in this situation. But now, let's take a look to the new bent line. The slope is standing for the fact that between current and voltage there is a linear relationship. A linear relationship. Do you notice that we are mentioning one fundamental law that you may know? Yes, it's the Ohm's law again. So we can substitute the diode here by a resistor standing for that slope. And the forward voltage, of course, because it begins here. Let's analyze the behavior of the diode at alternate current. The diode must be conducting. In fact, it is said that we have biased it at a certain point of the forward region of its characteristic. Then we can replace it by its brand new model that we have seen. As we are in alternate current, the V gamma or forward voltage drop disappears. Then we must focus only in the diode resistance R sub D. Who is R sub D? Let's focus in the bias point that we have achieved, the diode conducting in that particular current voltage values combination. Here, for instance, the current voltage related with Shockley equation at that bias point, and we move around that bias point with a small AC signal. This is why it is called small signal model. Let's zoom the bias point surroundings, okay? And bear in mind that we are moving just a few around this point. It's to say, we are using small signal approach. At this magnification, the exponential is very similar to a straight line, isn't it? We can assess an equation for this straight line. We are in a certain point, we are identifying a straight line with a slope in this equation, so this slope is, of course, the derivative of the exponential equation at this very bias point, the tangent line at this point. But this relationship current voltage as a straight line is the same as in Ohm's law. Then the behavior is exactly the same as the one of a resistor, as you can see. Current of the voltage is the inverse of that resistor. This is the dynamical resistance of the diode. Please notice that its value is a matter only of the values of voltage and current at the bias point. It is to say, DC values that are configuring the equivalent resistor of the diode at AC condition. There are many diodes in the market. Power diodes, with few currents moving through them. Signal diodes that try to modify electronic signals. LED, or light-emitting diodes, in which the recombination of electron-hole pairs lead to photons emissions. Or Zener diodes, where the Zener zone is used, without breakdown, to maintain a constant voltage value between cathode and anode in the reverse way. See you in the next video.